Okay, now since we all had some time implementing this function with MPI, we'll try to go back to the code and give a presentation how this may or may not work. So we have different possibilities. We could start from matrix multiply AVX. I guess should we use this one? Yeah, okay, good. Then, but what I will do is I will save this as AVX MPI, so that we use MPI and AVX together. Okay. By the way, I don't know whether I turned it off. Actually, I turned it off, yes. So I'm going to turn it on again. And maybe if it doesn't work, I turn it off again. So let's go back, activating the version with AVX. So I've not tried this, so I hope I hope this will work. So let us see. Right. Apparently we have not included the header for MPI yet, so we'll have to include. Now what did I do? Include MPI.header. So we have the header for MPI, so now we can use MPI. So there's stuff that we can keep reading, blah, allocate, generating the matrices, allocating the matrices. So I now take the liberty also, because we don't have that much time, that I will allocate these matrices everywhere, and then we can think about whether this is necessary if we still have some time. So we'll define it everywhere, we allocate it everywhere. And now we need to do some MPI specific stuff. So we'll have to have our rank, int rank, and we'll have the number of processes, num processes. Okay, maybe it's a good, it would be better to initialize them, but will initialize them with the function itself. MPI status. Okay, we can also ignore status, so this is not completely necessary. So then as we see in the picture, we'll have to have a local partial matrix A and a partial matrix C. Yeah, so which I'll call int. Yeah, always take care this is a pointer. Local A and also local B. Local C. What's
the typo? The asterisk should be, yeah.
Okay. I think this doesn't matter, but okay, Konstantin, does it matter? I think it does not, but let's do it this way. You see, yeah, it's a question, does this belong to the int or does it belong to the variable? Yeah. Apparently, you see, if this here is correct, then it belongs to the variable, because otherwise I didn't need to put it here again, right? Yeah. So okay, here I put it right. So I guess it's this way. So now these are the local variables. And then we have to do the MPI, the usual MPI stuff. So we'll have to have MPI init init, and this takes the command line arguments, which hopefully we named in the usual way. Yes, we did. This is then xc, and the other one we also named argv. So these are the same as the command line arguments, right? Okay, so this is the init, and then we'll have to determine our rank, MPI com rank, and we'll use MPI com world as always. Com, I don't know whether this always MPI com world, right? And we'll give the rank. So very similar to this, MPI com size, MPI com size, again MPI com world, and we called this numproc, numproc, yeah, numproc. Okay, so this is what we always have to do. And now we want to decide on how many rows we put into our local matrix. This is int rows per process. And what I'm going to do is I do a very simple integer division, n divided by num procs, and take note that this now will only work if this is divisible, yeah? But, don't consider the other part because this is more complicated. So now we have to do the allocation for the memory of the local variables. So we have local A, we have to allocate this int. So we'll allocate for an integer. We do malloc. So how big is this? This is the entire matrix is n times n, and this partial matrix is n times rows per process, right? So, and this times the size of what we are using. So you see, this is very low. This is very old-fashioned. This is why in new it will already know what size it takes. So this of course old-fashioned. So and the same we do for the same size we need for C. Do you have any questions there? No. Okay. So now we have a local A and a local C, and A, B, and C. These are still the global variables. Okay. Now we'll generate the matrices A and B, and this is something that now is supposed to happen only on the rank 0. So also we need this random number generator only here. So what we do is if we call this rank, yeah? We call if rank equals to 0. Always let me watch my. If rank is equal to 0, then we'll do this initialization, and also we do the okay, so now let us we'll also const auto start. No, that's not a good idea. Why is this not a good idea? Because then it will go out of scope, right? It will not remember it. Okay, so when we want to measure the time only on the in the process. Oh, no, okay, no, we can measure the time everywhere, and we only output it. Yes, doesn't matter. So everybody is measuring time. Okay, but only the rank 0 prints the matrix. So now, after printing the matrix, so I've seen some solutions where people try to do the broadcasting only if we are in rank 0. This is, of course, not correct. So all ranks have to call the broadcast, and the broadcast function itself will decide who is sending and who is receiving. Yeah. So now we need to get these things here around. We call MPI bcast. MPI bcast. So this is sending about the matrix B, and the matrix B has the size n times n. With MPI, see, this is a little bit the difference, a different interpretation. Malloc, the size of malloc was the number of elements times the size, so it's only how many bytes. Yeah, this here is taking the size and the kind and does the calculation for you, right? So this is the size of type, and now we want to gather. We want to broadcast things from rank 0 to the rest of the world. So here comes the root rank, and then we'll have to, as always, give the communicator, which again is com world. So, and that's it for broadcasting stuff. Then the matrix A has to be scattered. So this is MPI scatter, and this is taking the matrix A as, it's sending the matrix A, and it's sending A n times the number of elements per the number of rows per process. So it's not okay. This may be confusing. Yeah. In principle, it's sending the entire matrix, but here we are not saying how much it sends all together, but how big the chunks are that it sends. Okay. So we have the chunks. Then these come as MPI int. MPI int, right? So then this goes into, so where is it received? It is received in local A. Okay, it looks like we are doing overtime because we started too late. And here the chunk size is the same. It's rows and rows per process. And they also come in MPI int. Honestly, I don't know why we have to specify this here again, because it always is the same. Maybe there's something that I don't understand here. So our root rank is again 0, and we have to finish by giving the communicator, and the communicator is always com world. in our case. I mean, it can be different in other cases. Okay, so now we did the scatter. So everybody now should have what they need for doing the calculation. So now we have to do the proper calculation, and this is done in, now no longer in C, but in the local C. And the function, okay, in the local C, local C. Okay, skipping over this, and now we'll have to now we have to do the loop, and the loop is over the local A. Now the local A is of course smaller than the global A was. And this, do I have the right? Yes. So, okay, the thing that we are parallelizing is the rows, and the rows is the outer loop, right? So the rows, now it's not going until n, but it's going until rows per process, yeah? And the important thing here is now, we are doing two matrices. It does not matter where the matrix is. So we don't, because our matrix is actually, the A matrix, the new A matrix is actually smaller, yeah? Also the new C matrix, the local C matrix will be smaller. So we are looping over, not over the A matrix, but we are looping over the local A matrix, and therefore it is just smaller. So we still start at 0, right? Right, so now the thing we have to do differently is that we need to take in here the local A. The B is the same. Then we go through everything, and then we'll end up adding this again to the local C. Yeah, so this should do the job. And now we are done with our loop, and then we have to collect things again. So we have to do an MPI gather. MPI gather. So we take in here the local C. This is our result that we sent about. We sent number of rows times n of type MPI int. So the one that is receiving everything is the matrix C. Yeah, and the matrix C, so the amount that we want to receive is again the same. This is rows per process times n, and this again comes as an MPI int, and the root process again is 0, and we end with the communicator MPI communicator wait, no, this is not a good idea, world. So now everybody, no, the C matrix now should have been received at process 0, and the only thing that remains to be done, okay, not the only, there are a few more things. Then we want to print the matrix, but we only want to print the matrix if we are process 0, obviously. So we'll check whether if we are rank is 0, then we do this here. Okay, we'll have to. Then we do this here. And then, after everything is done, we free the memory. So we introduce two more things. I hope everybody has done this too. We have to free local A, and we have to free local B. So this has to be freed, and then there is one thing that remains to be done, which is what? MPI finalize. It's not B, it's C, right? Yes. So then MPI finalize. Otherwise, finalize. Oh, it's written this way. MPI finalize. Right. So, and then we should actually be done. Save. Let's see. So we are running a little bit over time potentially. We want to compile this, and this has to be done with MPI C++. Yeah. So we still have, because we are using AVX, we'll have to use this AVX here. The file that we take is now MPI, edit here, and call this MPI. Okay, and apparently I also have some optimization. Okay, it did not complain. Now we have to run it. This has to be done with MPI run, of course. When specifying the number of processes, now we have to make sure that this is divisible, otherwise we'll crash our code. Okay, we'll have a big matrix of 1,400. So if we do something like 4 or 8 or 16, so that should work. And then we go mat avx MPI. Let us see what's happening. Something runs. Okay, so apparently, let me see. Apparently my outputs, I was thinking, okay, so the runtime, right. Yeah, so I should, okay, so all of them gave out the runtime, so we could do this if rank equal to 0. So, and do it again. Okay, compiling it. So it was 0.79 seconds for 4 processes. Let's take 16. Okay, so it's faster, but not, not 4 times faster. Yeah. So now we are actually running out of time, but there's potentially one question that came up, namely whether we have to allocate the matrix A and C. Should we try this out? Because this will take another 5 or 10 minutes when we do not allocate them. Are you interested? Okay, then you see, we need, so what is our problem? The problem is in the gather function that has to be called by all of them, we need C, right? But, so the C needs to be specified, but the question is whether C needs to be allocated everywhere. Yeah, that's the difference. So let's what we could do then is the following. We can put A and C. Unfortunately, they are not next to each other. Yeah. So okay, I copied this and I just and I just take this out. So we could, for example, allocate, we do the allocation of this only if we are in rank 0. But we still have the matrix. We still declared it everywhere, right? So we'll have A allocated at 0 and C allocated at 0. Okay, maybe like this. So now it's only allocated in the 0 version, and then this of course means that we are not allowed to free. You are not allowed to free something that you have not allocated. Yeah. So we also have to put this here. So I'll comment this, and I free this here while I'm checking for rank 0. So, and now let's try this out, whether this actually works. I've not tried it. Let's. Okay, so it could be that it actually ran faster, but I think this is not related to this. So because the allocation was outside the time taking. Yeah. So anyway, you see, you need to give this pointer to the gather function always, but the memory needs to be allocated only on the process that is actually using it. Yeah. Okay, so that's it for today. I hope to see you next week again.